everyone. Today we have with us Arnab Bhattacharya for his talk on learning causal graphs and distribution testing. So Arnab was in fact formerly a professor here at IISc before going on to NUS. He is now a long-term visitor at the Simons Institute for Theory of Computing, which is where he is joining us from now. So he's won several awards through his career, like the most recent being his ACM Sigmoid Research Highlights Award. Prior to this, he has been an Amazon Faculty Research Award winner and also a Ramanujan Fellow when he was at IISc. So his education was completed from MIT, where he's done his PhD, and he was also a postdoctoral fellow at the Princeton University. So Arnab has worked widely on causality, distribution testing, and high dimensional statistics, apart from many allied questions relating to these areas. He recently released a book on property testing called Property Testing Problems and Techniques, along with Yuichi Yoshida, which you guys might consider reading. He is also part of the causality program at the Simons Institute, where he was at recently. He is published with some of the leading stalwarts in this area, and he promises to introduce us to some of the interesting open questions in this area of causality and distribution testing today. So without further ado, let me hand it to Arnab. All yours.
Okay, thank you. Yeah, it's very exciting for me to talk to you all. Yeah, I miss IISc a lot, and I hope to be back as soon as possible. Hopefully by the end of this year. Okay, so today I'm really excited to tell you about some of the work we have been doing in causality and to point you to some of the open directions. So this is going to be largely a survey talk, and I will go into like couple of things in some detail, and then some of the other things I'll just kind of mention at a high level what they are. And I mean, of course, if there's interest, we can talk after the presentation, and also I mean later, if you're interested, you can you can arrange a meeting with me and we can discuss anything of interest. Okay, so yeah, so the title of this talk is kind of long: algorithms for learning and testing high dimensional statistical and causal relations. But hopefully by the end of this presentation you will understand the general setup. So here, I mean, okay, so here is an example. So generally when we have a problem in data science, it often looks like this. So you have a sample, and each sample is a high dimensional vector. So you have, like for example, you have a cancer researcher, and the cancer researcher takes a patient and measures lots of variables. So like measures levels of some hormones, levels of some expression levels of some genes, presence of antibodies, presence of other growth factors, and then presence of tumors in the body. Okay, and she does this now. Okay, and n here throughout the talk, n is going to denote the number of variables, okay, or the dimension of each of the data. Okay, and of course the researcher does this not only for just one patient but for multiple patients, right? So you have all these patients, so you have all these vectors, n-dimensional vectors, which correspond to each patient. And then you could be asking two kinds of questions, and I want to really distinguish between these two different kinds of questions. One is a statistical question and one is a causal question. Okay, so the statistical question would be asking, in the data set, are say two variables independent or not, or like conditionally independent or not? So for example, here for some given thyroid hormone level, so basically you would be looking at only those samples in which that thyroid hormone level is at some particular value. Is can thyroid cancer independent of some growth signaling protein? So you would be looking at some two variables conditional on a third variable being at a certain value. And so this is a function. I mean, this the answer to this question is a function of the distribution of the data. Okay. A different kind of question, which we'll refer to as a causal question, is where you are asking what would happen if you change the system in some way. Okay, so suppose there's some treatment which inhibits expression of some growth factor and some proteins. How does it affect the likelihood of lung cancer? Okay, so this is so here you're not looking at the same distribution, you're asking what's often called an out of distribution question. So you're asking what would happen if there's a treatment which changes yeah, like the distribution in some way. So here it says it inhibits expression of these HER2 and fusion proteins. But I mean, of course, that could also change other variables through downstream effects. And then you ask, I mean, how it affects the likelihood of lung cancer. So statistical questions can be answered purely through understanding the distribution of the data, whereas if you have a causal question, then you also need to understand how the intervention mechanism. So here there's a treatment which is changing the system, how it changes the rest of the variables. Okay, I mean how kind of the manipulation of the system affects the distribution of the variables. Okay, and the main kind of perspective, the lens through which we look at these questions is through the lens of algorithms and finite sample complexity. So where we keep ourselves kind of keep our hands tied and say that we only have access to some finite amount of resources, and then we ask what is the best accuracy with which we can answer such questions. Okay. But before we even come to that, we have to first understand how to set up, I mean, like these two kinds of questions in a formal way. So let's just quickly do that. So the usual way of setting up these questions is to think of these variables. So like the n columns, right? So as being n random variables, x1 through xn. So each column is a random variable. It takes, I mean, so x1 takes the value in a random row, takes the value of the first coordinate in a random row. But of course, these are not independent, right? Because I mean, they come together in one sample and they are products of some grand physical process. Okay, and how do we describe this grand physical process? So the way usually this is done is through as like a basically a setup which goes back to Laplace in the 1800s, where he said that we envision the state of the universe as an effect of its past and as the cause of its future. Okay, and so basically he envisions a deterministic evolution of the universe, and this is how we are also going to think about these systems. So we have n variables, they are all connected to each other via these link functions which we call fi. So xi is fi of some subset of the parents, some subset of the variables which we think of as parents, and some unknown stochastic latent variable. Okay, so these functions fi are purely deterministic. It's just that the functions may depend on some other variables which we don't know, and those variables we think of as coming from some distribution. Okay, those are stochastic. Okay, the I mean, if we didn't have all information, then basically the universe evolves deterministically. But there are some pieces of information about the universe which we don't know, and those are modeled as random variables. Okay, so these xi's are functions of a subset of other variables which are called the parents, and some latent stochastic variables. So and the function fi, as I said, is deterministic. So and often these kind of systems will be described by causal diagrams where you have where the nodes correspond to the n variables. So you have here n is equal to 4, and so for each xi there is like a corresponding ui, which is the stochastic variable which goes into this function. But so when we don't draw a dotted line between two variables, that indicates that the ui, that the corresponding ui's are independent. So here u1, u2 and u4 would be independent, but the dotted line between x2 and x3 indicates that u2 and u3 are dependent. Without loss of generality, we can say that they're equal. So so this is what this indicates. Okay, so these functions, so the ui's may not be independent, but yeah, when we don't draw these arrows, these bidirected arcs, then they will indicate that they are that the ui's are independent. Okay, any okay, and yeah, this and when the ui's are dependent, this is what's known as confounding. Okay, maybe just let me give a quick example and then I'll pause to clarify things. So for example, here's a quick example. So you have two variables, x1 and x2. This is a causal system on two variables, and the evolution of these two variables, I talk about it as evolution in terms of time, but really there is no time in the formalism. It's basically you see the variables at a slice of time. Okay, so um, so these x1 and x2 depend on some unknown variable ui, u1. U1 and u2 are the same, and that's what this dotted arrow indicates. So here is a full description of this causal model. So for a full description, you would need to specify the distribution of the hidden variables. So here, for example, u1 is a random variable. It's a unbiased binary variable. X1 just copies u1, and x2 is x1 XOR u1. Okay, so now if you notice that when you observe the data, you will see x2 as always being 0, because x2 is just going to be x1 XOR x1, because u1 and x1 are identical. So x2 is 0. Okay, and so in terms of the distribution, you have that x1 is 1, 0 and 1 with probability half each, whereas x2 is 0 with probability 1. Okay, that is the distribution. Okay, but on the other hand, I mean, this causal model is more informative, because if you have this causal model at hand, you can reveal what happens when you have some intervention that externally manipulates the system and sets x1 to equal 0. Okay, so if x1 is set to equal to 0, then basically, so, and if this is done externally, right, this is, I'm not conditioning on x1 equal to 0, but but there is some active intervention. You should think of it as a treatment which goes in and forces x1 to take the value 0. If you do that, then basically u1 is not changed, so x2 has the value 0 XOR u1. So u1 is 0, 1 independent, so x2 becomes a coin flip. It's 0 with probability half and 1 with probability half. Okay, so I hope this makes it clear that the causal model is much more informative than just the joint distribution, because in the joint distribution, you just see that x2 is 0 with probability 1, and it would seem somewhat of a miracle that somehow changing x1 would suddenly make x2 to be a coin flip. But what's really going on is this causal model underneath. Okay, so maybe I'll just pause here for 1 minute and take any questions. Yeah, and by the way, I mean, I know that like this online medium kind of prevents, I mean, makes it harder to ask questions, but please interrupt me whenever you're confused.
Hi, Arnab. Quick question. Yeah, sorry, go ahead.
Yeah, so like typically you have these like a third variable in the graph, like the confounders are often like represented as a sort of third variable which you don't observe, but here you are, I think mathematically nothing changes, but here you're using this sort of a dotted arrow representation of it. So are the two somehow different, and I'm just missing?
No, they are identical. They're identical. Yeah.
Okay.
Yeah, so yeah, like you said, so
So
often you have like a Bayesian network on the whole set of variables, including the hidden variables. It's just that the hidden variables you don't see. So I am depicting it in a slightly different way, but they are identical. I mean, I just thought that this is a cleaner way to talk about it.
Sure, makes
I
sense.
mean,
And
with
you said,
functions being completely deterministic. Yeah, go ahead.
you said without loss of generality, you're assuming them to be like equal. Is that something obvious to see, or it just needs a bit of thought?
I mean, yeah, because basically, so x3 and x2 would depend on the.
Okay.
So if they're dependent, I mean, the maximum amount of dependence could be if they're equal. So you'll have the same information going
Sure.
into both.
Okay.
Yeah, that's all
Probably
I
you can
meant.
just
Yeah.
roll that aspect into like the function. Like if u3 was
Right.
some g of u2, you apply that g within f2 and
Right.
then kind of go through it. Okay.
Exactly. Yeah.
Yeah, makes sense.
There's another question.
Yeah. So in general, like, would we not need some UI with for every xi uh, for the model to be general. And just follow up would be, would you say an intervention is representable by a different causal model, uh, where in this particular example x1 is not dependent on u1?
Can you repeat the last question? I didn't quite get it. So
So,
you have a
so if you're working on x1, is that the same as, I guess it's the same as x1 not being dependent on u1 anymore? So it's a different distribution that you use for it.
I see. So you're saying that you could have two different causal models which result in the same intervention. Is that what you're saying? So x1 could just
No,
be x1 could
yeah.
you
So what?
could maybe you don't have an arrow from u1 to x1, but x1 is just independent, is like a coin flip separately. And
Yeah.
yeah, I mean, so right, I mean, it's not, I'm not claiming that this is the only causal model which generates this interventional I mean, this post intervention distribution. I mean, all that I'm saying is that observationally, if you just had the observation of x1 and x2, I mean, and you didn't have this description of the causal model, then you could not have predicted what would happen when I intervene x1 and set it to 0, right? That's all I'm saying.
Okay, thank you.
Okay. Yeah, and all this and more is discussed in great detail in Judea Pearl's book, Causality. So, I mean, if you're interested, I encourage you to look at it. Okay, so let me kind of go direct to kind of like the questions that we look at. Right, so throughout we'll assume that the causal diagram is acyclic. Okay, so there is an ordering in which you can invoke these functions, and they will give you the assignment of all the variables. And once you have such a functional causal model in your hand, it completely specifies the effects of exogenous treatments or interventions, right? Like I said, so basically the left hand side and right hand side of these equations are treated differently. So when you have an intervention, you affect the right hand side, but then that causes a different assignment to the left hand side. Okay, it's like, for example, in physics, when you have um, F equal to ma, actually, I mean, the way we think of it is as A equal to F over m. So when you apply a force, that causes a body to accelerate. Okay, and I mean, it's the same sort of philosophy that you have. Really, these equalities are assignments and not mathematical equalities, right? And intuitively, arguably, it captures what we mean by a causal process. Okay, uh, and just to kind of also give this notation, I mean, so when interpreted non-causally, so basically when you're just thinking of it as describing a distribution on the variables, these functional causal models are also called Bayes nets, and Bayes nets have been, I mean, used extensively to model distributions in many scenarios. Okay. But yeah, let me go to the kinds of questions, like the problems we look at. I mean, that will perhaps make all this more concrete. So throughout again, so we'll think of the asymptotic parameter as the dimension of the data. So n, the number of nodes, is asymptotically growing. And for statistical and computational reasons, we'll need to assume that the model is sparse in some sort of way. Okay, so we'll assume often that that the degree is bounded, and also that the dashed edges, I mean the confounder edges, have bounded span. Okay, so I won't define this formally now, but basically what you don't want to have is some sort of like god hidden variable which is affecting everything at once, and like this is an extremely high dimensional variable which affects all the variables in different ways, and if that happens, then it's basically impossible to predict results of interventions, because you'd have to fully know how that master variable is controlling everything. Okay, so you will need some sort of assumption to kind of rule that pathological situation out. and throughout we'll work with discrete variables over finite alphabet, but much of this theory could be extended to the continuous setting if you make parametric assumptions, but we won't really go there here. Okay, so let me tell you about two different kinds of problems that we are interested in. Okay, so one is what's known as causal or statistical estimation questions. Okay, so here the idea is that this diagram, the causal diagram, is already known to you. Okay, so you already know which variables depend on which variables, and what you're trying to learn is the distribution of the variables, okay, given the diagram, right? So so this is one of the core questions, learning the distribution, or you could be learning certain parameters of the distribution. Another problem, interesting problem here, is distance estimation, where you have two different um, distributions which are again described by given causal diagrams, and you are trying to estimate some sort of distance between the two distributions. Or you could be asking about hypothesis testing. So someone could give you I mean, yeah, like if you say again the diagram is known, but then you could be testing whether some parameter of the distribution takes on some value or not. Okay. Um, the other sort of questions which actually we will focus on this in this talk is statistical or causal discovery. Okay, so this is kind of the more kind of the exciting unknown frontier of this area, where we don't have the diagram in our hand. Okay, so the diagram is unknown, and you're trying to learn whatever we can about the structure from observational as well as possibly interventional data. Okay, and yeah, so this is structured learning, and then there's the analogous question of testing structure, where a scientist has some hypothetical structure in her hand, and she's trying to test or verify whether that structure is correct or not. Okay. um, okay, so maybe let's dive right in. So I'll first talk about the structure learning question, first from just purely observational data, and then I'll talk about a version of the structure learning question when you also have interventional data in your hand. Okay, so those are the two things I'll talk about in detail, and the rest I'll kind of sketch in whatever time I have. Okay, so throughout, whenever we talk about learning or testing, we'll be doing it approximately. And when you talk about approximation, you need to have some notion of distance. I mean, to tell how far you are away, how far away you are from the truth. Okay, so because we'll be outputting descriptions of distributions, we'll need measures of distances between distributions. Okay, and let me just quickly give two different notions of distances between distributions. One is the total variation metric, which is half of the L1 norm between the two probability mass functions. So here, remember that we are talking about discrete distributions. So these are just, I mean, finite sized objects. So you do the sum over a finite domain. And also you have KL divergence, which is not a metric, but a very useful notion of distance for information theoretic reasons. And this is defined like this. So it's basically the expectation over P of this log ratio, log of P of X over Q of X. Okay. Okay, so let's first go into the question of structured learning from observational data. Is there any other question before I start? Yeah, again, please interrupt me. I mean, please don't feel shy. Interrupt me when there's something which is unclear.
So,
Okay.
like just to sort of look at this slide one more time, the key difference between the two threads is the known, like whether the underlying graph is
Right.
known or not.
Yeah,
And
yeah. And this is kind of the key issue. I mean, that's what makes the discovery problem so hard, because you have this. I mean, the topological ordering of the variables is really what's the kind of the key computational difficulty.
and like when you say things like testing validity of parameters, that's just like things like whether the functions are this, or like the particular variable has
Right. I mean,
like something about
yeah,
UIs.
yeah, yeah. You could be asking, like, for example, say whether the I mean, you could be asking, say, conditional independence questions, whether like two subsets of variables are independent given another, or you could be checking whether the distribution of some subset of variables equals like your hypothesized distribution. Does that
Wait,
make sense?
does. But like, I mean, there's a big spectrum, right? In particular, even
Right.
if I know the underlying graph, like I might not know the functions or would know
Exactly.
only parts
Exactly.
of it and so on. So, okay.
Exactly. Yeah. So the first part, this distribution learning, is where you're trying to. So yeah, I mean, typically the way I like to think of it is I don't think of it in terms of learning the functions, because the functions itself they may not be unique, right? I mean, there could be different functions which result in the same
Huh.
output distribution. So we think of it as learning the distribution of the data, and so yeah, the functions are I mean, you learn some functions, or maybe it could be improper learning also, where you don't even
Hmm.
learn you don't even need to output a description in that particular I mean
Function class.
as that particular graph, but yeah, I mean, like but often typically these algorithms do what you're saying. I mean, you somehow try to do regression, like in this estimation you somehow try to do regression to try to
Hmm.
recover these functions approximately, and then you argue that these approximate answers you get for the FIs suffice to learn the distribution up to some error.
Right. And these are like, I guess maybe I'm stretching it too much, but questions like uncertainty among graphs and all that are, I would imagine, legitimate questions. I don't know the
Yeah,
exact graph, but I know that like it. I assume that it's
you
bounded
know,
degree or
yeah, I assume that is bounded degree, right? So there, so yeah, so this is basically more towards the discovery end. I mean, you need to make some assumptions about the graph, even, right?
right.
Because otherwise, yeah, these questions become just, I mean, too hard. So you need to make assumptions like a bounded degree, or maybe, I mean, like in the
Huh.
first part of the talk, I'll assume that the graph is a tree, for example. So it's
Right.
a very strong assumption, but you still don't know the graph, and you're trying to learn the graph um, with that assumption.
Correct. Okay. Yeah. Thanks.
Okay. So first, let me just say a word about generally learning high dimensional distributions. So the goal is that so here first let's forget about causality. Okay, so let's just think about learning the observational distribution. Okay, so you have a distribution, you're getting samples from that distribution, and it's high dimensional in the sense that the distribution is not like it's depicted here as a distribution on a line, but it's a distribution on an n-dimensional space. So each sample is an n-dimensional vector. Okay, and your goal is to output a description of a distribution p hat such that the total variation distance between p and p hat is at most epsilon. Okay, by the way, I mean, so I've used TV here, but there could be other notions of distance that could stand in its place. For example, there's this very interesting work by Guy Bressler and his collaborators, where they look at what's called local TV distance. So what local TV means is that only on every subset, like every subset of k variables, the distribution you learn, the marginal of the distribution you learn is close to the marginal of the true distribution. Okay, so it's kind of not learning the whole distribution up to TV error, but only learning but it suffices to I mean the distribution they learn gives good answers for every subset of k variables. Okay, or maybe some collection of subsets of variables. Okay, but there could be multiple notions of distance, but for now let's just stick to total variation. But this
Hi,
question
Arnab.
in general, yeah,
So just quick
yeah,
question. So
well,
you're outputting a
yeah,
p hat. When you say you want to output a p hat, you're outputting
yeah,
some joint distribution or interventional distribution.
yeah. Yeah, you're outputting. So forget about interventions right now. So I'm just talking about the observational distribution. So you're outputting a description of a joint distribution on the n variables.
Which is close enough you expect to p which is coming which you observe through a set of samples.
Exactly. Yeah.
Okay, thank you.
Yeah, so one thing is known that that just, I mean, information theoretically, if P is a distribution over the binary hypercube, then in general you need 2 to the n samples to learn P hat for any epsilon which is less than 1. Okay, so you need some assumptions about the form of the distribution. Okay, and so we will make assumptions about the so like the type of assumption we will make here is about the graph on which P is defined, right? So here is kind of the setup. So we'll assume that the um, P is being generated by a Bayes net on some unknown DAG G, but we'll assume that it has in degree at most D. So this is what Siddharth was also asking, that we make an assumption of this kind just to kind of make the to avoid the curse of dimensionality, and the goal is to output some G prime which is which describes a, I mean, on which there is a Bayes net with distribution P prime such that the P and P prime are close in TV distance. Okay, so this G prime may not exactly be G, but G prime admits a distribution P prime which is close to P. Okay, because again the goal being here to learn the distribution instead of to learn actually the graph G. Okay. Um, and it's actually known that with epsilon greater than 0 and for bounded D, the sample complexity now becomes from exponential in n to only linear in n times something which is exponential in the degree. Okay, but the this is nice, but the issue, I mean, which kind of plagues this area is that this is a sample complexity result and not a time complexity result. And indeed, I mean, this problem becomes hard when the degree becomes say at least appears to become hard when the problem when the dimension becomes more than 2. This is actually one of the central problems in this area, which I think is I feel it's really central, but it's not been resolved. So what is the computational hardness of this question that I wrote here formally, okay, in terms of computational complexity classes? So it's known that for epsilon equal to 0, recovering the exact graph, or recovering yeah, so like recovering the graph which can give the same P. So this is also what's known as recovering the Markov equivalence class of G. This is an NP hard problem when D becomes at least 3. Okay, but and yeah, so I mean, Chickering, Heckerman, Meek, they proved one version of this result, but it was kind of for the non-realizable case where P is not necessarily generated by a Bayes net, but P is some arbitrary Bayes net, and you are trying to decide whether it's being generated by a G with in degree at most D or not. So we recently extended this to the case where for this problem where you know that the input distribution is generated by a degree D Bayes net. But I mean, I actually still don't know what the answer is for positive epsilon. Okay, but problem definitely, I mean, is seems quite computationally challenging. I mean, I feel that the NP hardness, I mean, there should be hardness of approximation in the sense that even when epsilon is a constant, the problem should still be computationally hard. But there are other people who feel that there may be polynomial time algorithms to learn an approximate Bayes net. Okay, all right. So this is the situation for
Arnab,
yeah.
so you're not forcing G prime to have a bounded in degree, right? Like G prime can be, so it's
Yeah,
improper
G
learning
prime
in that
can,
sense.
yeah.
Okay.
Yeah, so what I'll talk about here is when we additionally assume that the okay, so here basically the degree is 1. So what what a tree means is that each node has at most one parent. Okay, so for the case when degree is equal to 1, we actually have nice answers, and this is what what will be the first part of this discussion. So the input is guaranteed to be from a distribution P, which is generated by a Bayes net on an unknown tree G. And here, yeah, I mean, you're not necessarily you don't need to output a tree, but we will. So you'll output a tree G prime on which there is a Bayes net with distribution P prime such that P and P prime are closed. Okay, and this problem actually has very classical roots. It was studied by these two gentlemen, Chow and Liu, in 1968, and so they gave the maximum likelihood tree. So the tree which has the highest likelihood of generating the data. I mean, if you had infinite amount of samples, and the Chow-Liu algorithm is widely used, for example, in the area of computational biology. But there was no kind of formal sample, finite sample guarantee prior to our work, and I mean, kind of very strangely concurrent with independent work of Daskalakis and Pan, we solved this problem last year. So where we showed that if the variables are taking values from a finite alphabet 1 through k, then Chow-Liu solves this problem, like the problem in the orange box, with high probability using order n over epsilon times k cubed samples. Okay, and this is nearly optimal in n and epsilon. The dependence on k is a rather interesting question, so we don't know the right answer there, but the dependence on n and epsilon are tight. Okay, so let me first show you like what is the kind of I mean this may seem rather uninformative, this n over epsilon times kq, but I'll tell you like what is the interesting part of this statement. Okay, so first of all, let me just set up some quick notation. So here actually for the analysis it's easier to look at KL divergence instead of TV, because you will see soon why. So let's define this okay, yeah, so let's define these two things. So if you have some particular tree T, okay, then and you have a distribution P, let's define the projection of P on T to be the closest T structured distribution Q in KL divergence. So it's you're taking a T structured distribution Q which minimizes the KL divergence between P and Q. Okay, and what we'll do is yeah, so in our case we want to, so we know P is a tree structure distribution, so we'll output a tree T hat such that the KL between P and P sub T hat is at most epsilon. Okay, so the closest distribution on T hat will have error will be at most epsilon away in KL from P. Okay, and so kind of the problem decouples into two parts. One is finding this T hat on which there is a P such that P and PT hat are close, and then the second part, that once you have a T hat, so this is like the estimation question where the structure is now fixed, so you have a T hat and then you are trying to find the closest P with respect to that T hat. Okay, so I'll show you the I mean, like we'll discuss the second problem where you're trying to find a T hat for so that the projection of P on T hat is at most epsilon away from P in KL divergence.
So, quick
And
question.
yeah,
May not
sorry, say that again.
are we guaranteed the existence of such a T hat?
I mean, we are assuming P is a tree structure distribution. So in fact, there's a tree T so that KL of P PT is 0.
Okay,
Right?
okay, yeah.
Because there is a tree, I mean, it is generated by some tree. So if you could output that tree, then I mean, P would be generated by that tree. So like the KL divergence would be 0 in that case. But here you're
Yeah.
outputting some T hat on which it may not, I mean, the closest distribution on T hat may not exactly equal P, but it's close to P.
Understood.
Is it
Thank
okay?
you. Yeah.
Okay. Yeah. And the reason that okay, so here is basically like all of Chow and Liu's paper in one slide. So basically what they show, and this is not so hard if you sit down and do it, that basically like you can, there's an explicit formula for the KL divergence between P and P sub S for any tree S. Okay, so what is that? So there's some constant which depends on P minus the sum over the pairs in sum over the edges in S of the mutual information between U and V. Okay, so the only way the tree S enters the picture is it determines the pairs on which you take the mutual information and you sum over these pairs. Okay, so it's clear, right? Like if I want to minimize this KL divergence, then basically I would try to maximize the sum of, so I would try to get a tree which maximizes the sum of these weights on the edges of that tree, where the weight of an edge is just the mutual information between the pair of variables. Okay, so I mean, yeah, like you can think back to your algorithms. I mean, your DAA class days, and basically like this problem is just the maximum weight spanning tree problem, right? So you're trying to find the tree which maximizes the sum of the weights, and this is, let me just quickly look at the time. Okay, yeah, so this is the maximum spanning tree. So this is Chow-Liu's algorithm, that you find the maximum spanning tree of mutual information between pairs of variables, and then you basically just return the tree. Okay, so I mean, and the key issue is that, like, in order to compute these mutual information, the weights on the edges, I mean, in the worst case, you would need, I mean, so like what Chow and Liu said is that if you could compute it exactly, then this T is the maximum likelihood tree. But of course, because we have finite number of samples, we only have approximations for each of these mutual information. And the question is that if we run the maximum spanning tree algorithm on these approximate weights, then what is the guarantee that we can get for the output of the algorithm? Okay. Um, okay. So maybe let me just quickly show like I mean, give you the flavor of the argument. Okay. So right. So basically, the point is that, I mean, okay, so there's kind of like a very naive way to look at this, right? So what you try to do is basically you guarantee that with the amount of samples you have, you estimate each of these mutual information to within a certain epsilon, and then like maybe you'd estimate each of these mutual information to within epsilon over n. And because the number of edges in the tree is at most n, the total error you would get for the sum would be at most epsilon, right? And for this kind of an argument to work, I mean, basically you need to understand how many samples you need to estimate the mutual information up to plus minus epsilon over n. And unfortunately, uh, you can show that approximating mutual information to plus minus epsilon over n requires n square over epsilon square samples. Okay, and this is actually not needed because, like I said, so the sample complexity we get, and this is nearly tight, is order n over epsilon, holding k a constant. Okay, so you have like a quadratic savings here, and this is why this result is interesting, because it beats the naive bound, which is n square over epsilon square, which just comes from estimating each of the mutual information in separately. Okay, so how do we get rid of this n square dependence? So basically, I mean, so this is the key fact, that somehow it turns out that, I mean, we need to use the structure of the tree. Okay, so let me just give you a quick toy example. So suppose T1 is the true tree. So your true tree is, I mean, Y is the root, and you have edges from Y to X and Y to Z. And suppose you output T2, which is the output tree, which is the tree that's output by Chow-Liu. Okay, and so here you are outputting X, Z2X and Z2Y. Okay, so you can show that, I mean, if this T1 is the true tree, then the KL divergence between P and PT2, which is the best distribution on T2 for P, this is basically I of XY, which is the edge which is in T1 but not in T2, minus I of XZ, which is the edge which is not in T1 but in T2. And yeah, so basically, so this is the main claim. Okay, so and this is the interesting claim. So basically what this is saying is that if I of xy minus I of xz is at least epsilon, so if this was less than epsilon, then the problem goes away, because then if this difference between I of xy minus I of xz is less than epsilon, then basically it is saying that T2 is also a good enough tree, because the P and PT2 would also be at most KL in a KL divergence. Okay, so the bad case is when this gap is large. So I of xy minus I of xz is large. Okay, so then with only order 1 over epsilon samples, I mean I of x hat y hat, which is the empirical mutual information, minus I of x hat z hat is greater than 0. Okay, and once you have it's greater than 0, then basically that means that Chow-Liu will never pick xz over xy, right? So it will pick xy over xz because it's finding the maximum weight spanning tree, right? uh, and uh, and right, so this is, I mean, and this is non-trivial, because I mean, like, the naive way to prove this claim would be to say that with the sample number of samples you get, I of xy you estimate up to plus minus epsilon over 2, I of xz you estimate up to plus minus epsilon over 2, so that then this new difference does not get to less than 0. Okay, but that would require 1 over epsilon square samples. And the key point here is that we show that only with order 1 over epsilon samples, this, I mean, you maintain that the difference stays positive. Okay, and this is what's in this bullet. Okay, and the way we do it is basically by reducing it to a testing problem. So what we show is that, so this, yeah, so essentially what happens is that this I of xy minus I of xz is really, you can use the data processing or basically the chain rule for mutual information to write it as the difference of conditional mutual information. And here you use the fact that because the data is generated from T1, I of xzy, this second bullet, is actually 0. Okay, this is 0 for the true distribution. It's not 0 for the empirical distribution. And yeah, so then this is the fact. So basically you say that if you have a tester, okay, so what a tester is, that means is that it's not learning each mutual information to up to plus minus epsilon. It's only distinguishing between whether the mutual information is 0 or at least epsilon. Okay, so here in the empirical, I mean, like in the true distribution, this conditional mutual information I of xz condition on y, this was 0, and you can say that it doesn't become more than epsilon if you take order 1 over epsilon samples. And on the other hand, you also have that yeah, so it was 0 originally and it doesn't become more than epsilon over 2, let's say. And we then also know that this guy must be at least epsilon, because this difference is at least epsilon. So this is at least epsilon, since this is 0, this is at least epsilon. And the tester maintains that if it was at least epsilon, then then after you take these samples, then I mean, you can distinguish between 0 and epsilon. So this stays something small and this stays something large. So the gap is still positive. Okay, and this argument essentially extends to n variables using simple properties of the of maximum spanning trees. Okay, so any quick questions? I guess I'm running out of time. I have like maybe 10 minutes. Is that okay, Siddharth?
Yes, yeah. Take your time. Yeah.
Okay, yeah. Um, yeah, but if there are quick questions, I can take it here or I can take it after the presentation. Okay. Yeah, so the key, I mean, the key takeaway here is that, like, this is the core of the technical part. I mean, we show that you can test uh, whether the conditional mutual information is 0 or epsilon using k square over epsilon samples. Okay, and the tester is nothing but just a threshold on the empirical mutual information. So it's really simple. So you just take the empirical mutual information and you test whether it's more than some threshold. If it's more than some threshold, you say it's a second case. If it's less than the threshold, you say it's zero. And and the key point is that we reduce to this testing question instead of the harder learning question. Like I said, I mean, if you wanted to estimate each of the mutual information to within epsilon over 2, this would take you 1 over epsilon square samples. Okay, and this epsilon is important because this epsilon becomes epsilon over n once you apply it to this n-dimensional distribution. Like I said, the dependence on k actually we don't know. So this is a really interesting question, I feel. Actually, there's a typo. This should be k cubed and not k squared. The k square is for the mutual information where you're not conditioning on any variable. Okay, and it turned out that before our work, there was no optimal tester, also known for this case, when you're just testing whether the mutual information between two variables is 0 or more than epsilon, right? And yeah, so our work shows that it can be done in k square over epsilon samples. We think the k square should actually be k, but we don't have proof.
Yeah, Arnab, I'll ask a question, but please feel free to defer it to the end in the interest of time. So
Okay.
what we have is that there is a distribution P generated by some unknown tree G, and you
Yeah.
are now the output of the algorithm in a sample efficient and a computationally efficient manner is a tree G prime with a distribution P prime. So I guess the
Right.
functions also sort of the FIs come out of this sort of mutual
Yeah.
information
So this
estimate.
is the second part. So yeah. So this is also an interesting question which I'm not talking about here. So once you have the tree, you'd like to recover the distribution, right? And this is basically what you. So you know the parents. So what you can try to do is you can learn the conditional distribution of each variable conditioned on its parent variable, right? Like on its
Okay.
parent variable being 0 and its parent variable being 1. So you can learn that conditional distribution, which is basically learning the FIs.
Uh-huh.
And you need to show that like if you learn those conditional distributions up to some error, then you can put it all together in order to do in order to get a bound on the whole distribution. This is also not entirely trivial, and I mean there is work there, but I'm not describing it here.
Okay. But what I'm curious of, and maybe best left to the end, is what does this tell me about interventional distribution? So
Yeah. Yeah. Okay, so maybe yeah, we can keep that for later. I'll also
sure.
yeah, so I'll next talk about interventions. So yeah, in the remaining I guess 7 or 8 minutes, let me just quickly mention some new work. I mean, it's not published yet on learning from. So this is learning from interventions, um, but here you're trying to learn the causal model. Okay, and I mean the motivation is that I mean, like, I think if you go to any talk on causality, at some point you'll hear about smoking and lung cancer. But basically there is a I mean yeah, this was a real life story which happened where people were trying to find out the connection between smoking and lung cancer. There was a study which showed that smokers are 4 times more likely to get lung cancer than non-smokers. But then Ronald Fisher, um, like the father of modern statistics and also a passionate smoker, he I mean he pointed out that of course it could be other things. I mean, it could be that maybe people start smoking in order to reduce the pain they get from lung cancer, or maybe it could be that there's some gene which causes people to both like smoking and also to get lung cancer. I mean, of course, there are kind of bogus reasons, but his point was to kind of emphasize that you need to do randomized control trials in order to find out the arrow of causality, right? So in particular, if you have these three alternatives, so suppose it's either x causes y or y causes x, or there's a confounder which is causing both x and y, then if you want to distinguish between these three possibilities, what you can do is you can do an intervention. So if you intervene on x, then it would change the marginal on y, but doing on y would not change x, vice versa for y to x. And if this is the situation where there's a third variable which is causing both x and y, then basically an intervention on either x or y will not change the other variable, right? So using interventions, you can clearly distinguish between these three alternatives. Using observations, it's impossible. And the question, so this is of course like a very classical fact, and what we were interested in, I mean, is there some way that we can understand this basic setup like in a finite sample complexity setting? Okay, so how many samples from observational and interventional distributions do we need in order to determine the truth? Okay, and can we save on interventional samples if we take more observational samples? Okay, um, and yeah, this is exactly the question that we answer in a joint work with Jaydev Acharya, Saurabh Bhatane, Sarvanan Kandasamy, who was a master's student at IISc, and Ziteng Sun. And I feel like our answers, I mean, like we don't even have the full picture yet, even for this two variable setting. But I feel like that this direction is super interesting, and that's why I wanted to mention it in this talk. So suppose x and y are random variables on 1 through k. Okay, so what we show is that there's a trade-off between the number of samples you get from observational distributions and the number of samples you get from interventional distributions. In particular, if you make k to the c many observational distribution observational samples, then you need to take okay, this should be a min, not a max, I think. Is it? Oh wait, let me just think. Sorry, it's a max. Yeah, max. Sorry. So basically, you need to take at least square root k samples from interventional distributions, even if c becomes 1. But uh, but if c is but you can reduce. So for example, if c is equal to 2/3, then you make k to the 2/3 many observational samples and k to the 2/3 many interventional samples. Okay, but as you make c be more than 2/3, you can reduce the number of samples you take from interventions. Okay, um, and this I think is quite fascinating, because like I said, it's common wisdom that you need to take you need to do interventions in order to find the causal structure. But actually, like this finite sample complexity points out that there's kind of a richer picture, that if you have more than required number of observational samples, you can reduce your dependency on the number of interventional samples. Okay, so here when I talk about interventional samples, it means that you do I mean, you do a certain number of interventions, and for each intervention you draw samples from the resulting distribution, and this interventional samples is the sum over all the samples you draw from all the interventions. Okay, in fact, the total number of distinct interventions is constant. It depends only on epsilon and not on k, which is the growing parameter in this setup. Yeah, so that doesn't factor in much actually. Okay. And
Hi.
yeah, go ahead.
Does it matter what kind of observations are there, or independent of observations are that's sufficient?
So the observations are coming from a distribution on these two variables. So they are it's like on a distribution on a space of size k squared. So each x and y are on 1 through k. So this is p is a joint distribution on k cross k. So p is
Right.
any such joint distribution. So we
Suppose
assume that p is far from a product. So the epsilon here is that it's far from a product distribution. So if it's product, then basically the picture is just that the graph is empty. So we assume that the variables are correlated, but we don't know which way the direction of the causal arrow goes.
thank you.
Yeah. Okay. Um, yeah. So maybe I'll just yeah, I'll just kind of briefly give you the punchline. So the idea is just that we reduce to this question of closeness testing. Okay, so where you are testing whether the marginal distribution uh, equals the interventional distribution or not. Okay, so for example here, if the marginal distribution equals the interventional distribution, that means that the arrow, that means that it's not like this y to x, because um, you're intervening on y, but it doesn't change the distribution on x. Okay. On the other hand, if the so on the other hand, if the TV distance was at least epsilon, then we would know that the picture is actually this arrow from y to x. Okay, so you reduce it to closeness testing, and then we can use as previous work, which actually says that there is a trade-off in closeness testing. So here the question is really simple. You just have two distributions P and Q, and you're trying to test whether P equals Q or P is far from Q. Okay, and this result says that if you take more samples from P, you can reduce the number of samples from Q. So if M1 becomes large, then M2 becomes K over root M1. M1 is the number of samples from P and M2 from Q. Okay, but again, of course, there's some lower bound which is required on the number of samples from Q. But if you go more than this lower bound, then there's a trade-off. Okay? This is a work by Bhattacharyya and Valiant. This is a different Bhattacharyya with a single Y, not two Ys like mine. Okay. And more generally, it actually gives rise to this problem where you have a sample access to three distributions: the marginal distribution, the conditional distribution, and the interventional distribution, where you know that P and Q are far. So this is coming from the assumption that the distribution is far from product. So conditioning on one of the variables makes the other variable have a different distribution than the marginal. So P and Q are far, and you are trying to test whether R equals P or R equals to Q. Okay, and the full sample complexity in this setup is actually not completely understood. Okay, so this trade-off that I gave is only valid for this is actually tight when in a certain regime. But for example, when the number of observational distributions is super high, like you make K over epsilon square many samples, then basically you know the observational distribution completely, and there you can do what's known as density estimation. So there you need only 1 over epsilon square samples from interventions. So in fact, there's kind of like a very rich picture about how the sample complexities of like what is the trade-offs between the observational samples and the interventional samples that we don't fully understand. Okay, and one of my long-term goals is to kind of develop a refined understanding of the structural learning problem in terms of trade-offs between observational and interventional samples, and not just use the common wisdom that you need interventions. Of course you need interventions, but you can reduce their dependence on them if you have access to more cheaply available information. Okay, so maybe let me just stop here, and if there's interest, I can send the slides, and if people have questions, I can definitely answer. Thank you, everyone.
Thank you.
Thank you.
Thanks, Arnab, for the talk. If anyone has questions, we'll take them now.
What about lower bounds, like in this like bi-criterion sort of? So if I
for the second problem I talked about,
right, so let's say you have a
so we do
budget
have
on
right. So we do have some lower bounds. So like that trade-off that I mentioned between the k to the c and k to the 1 minus c over 2, we do know it's also tight, basically because because for the closeness testing problem also there are optimality results, but that's only tightness in a certain regime. We actually still don't know the full picture over all possible values of over the full spectrum of the observational samples. Um, but but also I think, right, so your other question was if you have a budget, right? So if you have a combined budget on how many, so generally speaking, interventional samples are harder to obtain than observational ones, so you can
right.
put like higher cost on those. So again, there has been some work on this also in my group, but this is more with infinite samples, and there you're just trying to find. So you have a cost for an intervention, and you're trying to minimize the number of interventions, not
Right.
really minimize the number of samples that you draw from intervention, but you have a cost for an intervention, and you're trying to minimize the total cost of the interventions. Yeah, I think it's a really interesting problem to also assign. I mean, because at the end of the day, you only get samples from. I mean, you do an experiment and you get samples, right? So this is really the cost. So yeah, I think it would. I mean, that would also be a very interesting study. I mean, this is just what that kind of is in the pipeline. So we definitely have not gone there yet.
Yeah, maybe I'll stop, but after the recording, it'd be great if you can like, speak, like say a few words about like this counterfact, the other two problems that you have mentioned earlier.
Sure. Yeah.
Yeah.
Okay.
So following up on my question that I was asking in talk, I was just wondering if this, so your research is clearly independent of. Uh, so I'm guessing like the lower bound might have some worst case distribution from where the samples are coming. Or in other words,
Sorry.
if you make
Which problem are you talking about? The second problem.
second problem, so we are seeing
Okay.
if you go back to maybe I can point out, you're saying there is like a certain of distributions coming.
Uh,
The inference.
too many slides. 1 second. Yeah.
Yeah. So here, effectively, you're saying this is independent of the distribution from which it's coming. Like, so for example, I was just wondering, what if there's a distribution where you don't get
Yeah.
sample for a particular variant, a particular set of
Can you say that again? You're breaking up. You don't get samples for a particular what?
particular values of x and y.
Oh, you mean there's some sort of selection bias, so you don't see
You
um,
don't see,
like some of the samples are removed.
yes, yes. No, I'm saying this. There
Okay.
is a where you don't see certain values of x and y much, and then you'll have to go and intervene on that. And then your made your theorem is independent of p. So I was just wondering whether you have a worst case distribution p or
Yeah, so basically, I mean, here I mean, it's a distribution on a k-square values, right? So usually you need to make assumptions about p, about like structural assumptions about p. Usually they are done in more parametric settings, like if you are looking at continuous densities, there you definitely it's much more important to make structural restrictions on p. So here, because it's like only on two variables, we don't really need to put any assumption on p. Um, I mean, I think there are two different answers to your question. So one is, okay, so one question is that like if you have some situation in which you don't see certain samples, like some of the samples are removed, if x and y take some particular values, then those samples are removed. This is a beautiful question. So this is what's known as when you have truncation in the sampling process. And yeah, this is another line of work that I've been pursuing, where you I mean, it's also related to causality because it talks about the data generating process, where you have like you have a generator which is generating the true samples, and then what you're observing is a subset of those samples. And like the
yeah.
observation may not be at random, it may not be that just random samples are thrown away. It could be that some samples are thrown away for very particular reasons, right? Like it could be that maybe there's some sensitive data or something like that for which those samples cannot be revealed, or maybe like the person who is answering the questions on a form, they don't report if the answer to some question is yes. Okay, so so basically this is what's called self-selection or sampling bias, where basically you have bias in the observation process. And it's a beautiful question, I mean, to try to recover the parameters of the distribution from truncated samples. So this is one aspect. The other, I think, aspect you're talking about is, I mean, what does P look like for in the worst case? So when we talk about lower bounds, we need to give, we need to kind of specify like what the hard P is, for which I mean, this trade-off is tight. So that distribution basically looks like, um, I'm trying to remember. So essentially, basically, yeah, I think one of the distribution is uniform. The other is that you choose. I mean, there's something called this Paninsky distribution, where basically like you choose pairs of elements, and then for those pairs of elements, you randomly make one of them be more biased than the other. Like you make one of them be half plus epsilon, one of them be half minus epsilon. And so this is kind of like a classical construction in the distribution testing setup, and we kind of adapt that hard instance to get a lower bound for our theorem. Sorry, maybe that was too long-winded.
No, I appreciate it. I'll stop the
Okay,
recording.
yeah, I mean, our paper is going to be out soon, so I mean, like within the next week or so. So, yeah. So I mean, you can find full details there.
I had one question related to the theorem.
Sure.
So, like, what do we mean by total number of distinct interventions? Like, are we saying that P of Y do X is one intervention and do Y is the second intervention, or do X equal
No,
to
do
X1?
x. Yeah, do x equal to something, right? Like you are setting x equal to some value. So you need to specify what that value is.
So, do X
Does
equal
that
to
make sense?
X1 and do X equal to X2 are two distinct interventions.
Are two distinct interventions, yeah. But when I say interventional samples, I add up the samples from all these interventions.
Okay.
I mean, anyway, the number of interventions is a constant, doesn't depend on k. So yeah, so up to constant factors, I'm just looking at the maximum number of samples I'm taking from any intervention.
But like, is this just true for these simple graphs, or for even for like linear graphs, it will be true?
What will be true?
That the number of distinct intervention would be independent of k.
No. I mean, this is only true for the two variable case. Yeah, I mean, like this kind of theorem, we don't have an analog for more general situations, and this is also a very interesting line of research. Okay, so are there other questions, and I can also answer? Yeah, please go ahead.